For centuries, humanity has gazed at the cosmos, at the dazzling dance of stars and distant galaxies, the majestic clouds of nebulae where new worlds are born, and felt a profound connection to the visible universe. We've measured its distances, studied its elements, mapped its grand tapestry. We've come to understand so much about the light that reaches our eyes and the matter that makes up everything we can touch, see, and sense. But what if I told you that everything we've ever observed, every star, every planet, every glowing nebula, all of it, account for only a tiny fraction of what's truly out there? That the universe we interact with, the one filled with light and heat, is just 5% of reality. The vast majority, a staggering 95%, remains invisible, a profound mystery shaping everything around us. These are the cosmic ghosts, dark matter, the unseen gravitational glue that holds galaxies together, and dark energy, the mysterious force accelerating the universe's expansion, tearing it apart. Tonight, we journey into the heart of this enigma. We'll explore the evidence for these invisible architects, the theories attempting to explain them, and why they represent the greatest challenge and the greatest opportunity in modern astrophysics. Our story begins not in theory, but with a puzzle in the data. In the 1970s, pioneering astronomer Vera Rubin was studying how galaxies spin. We expected stars on the outer edges to move slower than those closer to the center, just like planets in our solar system. The farther a planet is from the sun, the slower it orbits. But what Vera Rubin found was completely different. The stars on the outer edges were moving at the same incredible speed as the stars in the core. It was as if an invisible gravitational anchor was holding the entire galaxy together, preventing it from simply flying apart. This was our first major clue. Scientists found even more powerful evidence in a phenomenon predicted by Einstein himself: gravitational lensing. According to his theory of general relativity, massive objects warp the fabric of space-time. This means that a huge galaxy or cluster can act like a giant lens, bending the light from objects far behind it. But the lensing we observed was far too strong to be caused by just the visible stars and gas. This provided us with a direct way to weigh the invisible matter. The amount of light bending required a massive amount of unseen substance, far more than all the visible galaxies combined. This confirmed what the galaxy rotation study suggested. Something truly invisible was out there, and it was the dominant gravitational force in the universe. For a long time, we thought the universe's destiny was straightforward. The initial expansion from the Big Bang should have been slowing down over billions of years, pulled back by the combined gravity of all the stars and galaxies. It was like throwing a ball into the air, expecting it to slow down and eventually fall back to Earth. But in the late 1990s, two separate teams of astronomers were using distant supernovas to measure the universe's expansion. They were looking for the cosmic slowdown, but what they found was completely the opposite. Instead of slowing down, the universe's expansion was accelerating. These exploding stars, known as Type I supernovas, act as standard candles because they always burn with the same intrinsic brightness. By comparing their observed brightness to their known brightness, scientists could accurately measure their distance and, in turn, the expansion of the universe. The data revealed a shocking truth. The distant supernovas were much fainter than they should have been, meaning they were much farther away. This accelerating expansion demanded an explanation. To solve this mystery, a new kind of energy was proposed, a pervasive, repulsive force woven into the very fabric of space. We call this force dark energy. Unlike dark matter, which acts like a cosmic glue, dark energy acts like a cosmic anti-gravity. It's the engine driving the universe apart, dominating its ultimate fate and making up roughly 68% of its total energy content. Together, dark matter and dark energy represent the unseen 95% of our cosmos. So, if we can't see them, what could they be? For dark matter, the leading theory suggests it's made of exotic, new subatomic particles that interact with normal matter only through gravity. Scientists are actively searching for these particles in underground labs and particle accelerators like the Large Hadron Collider. But dark energy is an even greater mystery. The leading idea, which dates back to Einstein, is a cosmological constant, a repulsive energy that is an intrinsic property of space itself. As the universe expands, more space is created, and with it, more dark energy, which drives even faster expansion. So what have we learned? That our cosmos is a realm of two dueling, invisible forces. Dark matter, the gravitational scaffolding, holds galaxies together and makes up 27% of the universe. And dark energy, the accelerating force, is pushing space apart and accounts for a staggering 68%. The fact that 95% of the universe is still a mystery is not a failure of science, but a testament to how much more there is to explore. With next-generation telescopes and ambitious space missions, we are on the verge of new discoveries. These invisible forces remind us that our understanding of the cosmos is far from complete. The greatest discoveries often lie not in what we can see, but in the shadows, waiting for us to finally pull back the veil.